Hey, so we spoke about regression and correlation till now, and where we have a y versus x situation. Now we're going to talk about a really specific case of y versus x, which is the time series. Now the time series, unlike the regression and correlation where we were so adamant that we have to have independent samples, the time series is no longer independent. We have an x-axis, which is always time, and we have a y-axis, which is a measurement taken at different time points, but it's usually from the same place or the same region or the same instrument, giving us a record of measurements over time. Now the frequency of that measurement can vary a lot. We can have things that are measured annually. We can have things like in all these types of data loggers that get measured at frequencies that are higher than once a second. Here's a time series example, and this is mean sea level in Honolulu in Hawaii. And the trend here, we see a rise in sea level. We're seeing a lot of variation around this trend. What we can see on the y-axis is the meters on the tide gauge versus time, and in this case these are years. So different ports especially have tide gauges in them because we're interested to know when ships can come in and not come into port. And some of these places around the world go back more than a century, or sometimes more than 2 centuries, so we can have a really long-term record of what happened with sea level. So these days tide gauges measure at very high frequencies. We can have every few minutes a measurement of sea level at that location. And this feeds into tide models and into how we know what the high tide does, what the low tide does, when. But what we get from it as well is this long-term trend that we're interested in of knowing what's happened to global sea levels over this last period of anthropogenically caused warming. Other types of, so you've seen a lot of time series to do with global warming, so we're seeing a lot of things like sea level and temperature over time. But we use time series data in a lot of different situations. So here is a tree, and on this tree sits this data recorder that's connected to this aluminium band, and the band expands and contracts with the tree. There's a spring on it. Now there are reasons for the tree to expand. One is just growth over time. The tree is growing and accumulating wood. And another reason is water. So when the tree is transpiring, taking up water from the soil into the leaves, and this is happening in daytime, it expands a bit because it swells with the water. At nighttime, when this process isn't happening, the tree contracts a bit. So if we look at this time series, again, the x is time, and in this case it's hours from some point that it was installed. And this is the diameter of the tree. We're seeing 2 things here. One is a trend that is increasing because the tree is growing. And we also see some variations. Sometimes we're really interested in both these things, both in what's happening in the long-term kind of trajectory. And another thing we're interested in is those seasonality or cyclical causes for change. Time series are used to explain a lot of earthquake activity or seismic activity. So seismic activity can be caused by a lot of things. One of it is earthquakes, and earthquakes have a really unique spectral time signature. So here this is how everything's shaking. So, you know, I mean, like your house shakes when a train goes by if you live close to the tracks. Your house shakes when a jet plane goes overhead. But an earthquake shakes your house in a certain manner. And it has a time series. Again, time is here, and this time it's in seconds. And here is the change on the seismograph, and we have these vibrations at first and then some bigger vibrations. So we have a first phase of the earthquake and a second phase. So we have these time series, and what we do is basically detect trends and other patterns that occur over time. So we're interested both in the trend, but also in the pattern that surrounds this trend. So we have repeated measures of a variable at successive time points. Okay, so it could be the weather, it could be the sea level, it could be the seismograph, it could be the dendrometer band. Doesn't matter. It could be the string gauging. It's just that we have an x that is time. So unlike other x's, time series objects in R, for example, are defined slightly differently because they are a time series. So we need to convert our data. So if I have data that is this, just a regular vector, I can create a time series from it. And I use the function ts to tell my variable that it is a time series variable, and actually the frequency of measurement is, in this case, monthly. Okay, I measure 12 times a year. The series starts from 1958. So what's happening here is it's creating an x-axis that will have monthly intervals starting 1958 to match with this y data, with this measured variable. So this is for monthly. If it's annually, I'm going to have a frequency of 1. If it's daily, I'm going to have a frequency of 365. If it's quarterly data, a lot of time series for financial products come in quarterly data, so we have a frequency of 4. Okay, 4 times a year. Monthly is 12 times a year. Okay, and this is when my time series started in this case. So what can I do with now I have a time series, what can I do with it? So first of all, what we're going to do next is what we call the descriptive analysis. So we're going to look at what is the trend. Is there a trend in my time series? Is it increasing? Is it decreasing? Or is it a stationary time series? Is it not changing over time? Is there no trend over time? And we're going to use some more complex techniques to tell us what those are. We're going to look at what the cyclical patterns in the time series are. Are there things that are repeating predictably? And if so, at what frequency? How frequently do events return? We're going to see how we determine outliers in the time series. Those are sometimes really important because they are that 1 year where something interesting happened, and it tells you a lot about the system. So say a volcano goes off and it affects the world's climate. We're going to see this in the long-term time series, and it's going to be something that's superimposed on the regular trend and cycles. And then we learn something. We learn that, if this happens to our atmosphere, this is the outcome. Another thing we're interested a lot in, especially in things related to climate change, is turning points in the time series. So say we were bumbling along at a certain rate and with certain cycles, and all of a sudden things have changed. Okay, so we have these turning points, and we'd like to identify them. But suddenly the cycles are different, or maybe the trend becomes different. So we have that quite frequently in areas that are coastal, where areas that were previously not inundated are now inundated, and we see changes to, say, growth rates in the trees. The next step we're going to look at is the spectral analysis, and we'll do that next lecture. But this is carried out on the cyclical pattern to work out what frequencies are accounted for in this cyclical component. So are there things that are monthly? Are there things that are once a year? Are there things that come about, like a seasonal cycle, like there's winter once a year? Is it something that is over many years? Are there, we know there are cycles driving our climate that are thousands of years and tens of thousands of years apart, right? So if we think about glaciation events during the Pleistocene, we know that things happened at frequencies of 100,000 years and previously 40,000 years, right? So we can analyze these plots using spectral analysis, and or sometimes it's called frequency domain. We'll spend quite a bit of time on those. Two things we're not going to talk about in this unit because they're kind of beyond the scope of basic time series analysis is forecasting. So often we want to know the trend, and we want to understand the patterns we can predict so that we can forecast into the future. A lot of our IPCC data is doing just that. We're trying to work out what things are going to be like in 2100 under different scenarios. And intervention analysis, that other one that does analyses that identify these turning points. So those two things we're not really going to talk about, but the first two we're going to go in a great detail. And I'm going to start with decomposing the time series. So decomposing the time series is, as it says on the box, we have a time series. This time series is made up of a lot of things going on at the same time, and we're going to decompose that into its different components. We have things called the seasonal components. So what we see here is the Keeling curve. So this is the atmospheric CO2 concentrations measured on Mauna Loa in Hawaii, and these are the years of measurements, okay, time series of CO2 concentrations in the atmosphere. Here we are, where we are consistently above 400 all year round, and we started off at about 280 in the pre-industrial, right? So what you can see here straight away is that there is a trend, and it's an upwards trend. That's what we're trying to, curb now. And there's another thing which is happening, which is the seasonal component. There's some fluctuation that's happening regularly. There are peaks that are spaced regularly, and actually the amplitude of those peaks is also quite regular. This is summer-winter, okay? Because in the summer, in the northern hemisphere, we have a lot of forests. They take up a lot of CO2. And then in the winter, they shed their leaves, okay, they're deciduous, they do nothing. We have more CO2 in the atmosphere that's not captured by the plants. Okay, so what you're seeing here is basically the world breathing in, breathing out seasonally. So by decomposing, we can extract the seasonal component, also called cyclical component. We usually use the word seasonal component for what we know as the seasons, as that's our annual cycle. Cyclical component does not necessarily dictate that. Those two are used sometimes interchangeably. So seasonal components are a cyclical component, but sometimes we have more than one cyclical component going through the data, so we can have seasonal plus some sort of longer term cyclical component. Okay, so one that's over many years. We have 10 good years, 10 bad years, 10 good years. Then we have the trend component that we want to know, which is the CO2 rising over time. And we want to identify all sorts of irregular components. Okay? In this case, we have a level, which is here, which is the average value in the time series. So this is where our time series levels. And when we have a trend, we have deviation from this level. But in a stationary time series, so one not like CO2, this trend is basically around the level the whole time. Now we've seen a lot of upward trends in sea level and CO2. We have downward trends just as much. If we think about biodiversity on the planet, we're seeing a really strong downward trend in that, unfortunately. We see that downward trends as well in time series. It's just not presented as often, unfortunately. So how do I go about decomposing this time series? What I'm telling you here is relevant to what we call the additive model. Okay, and I'm going to come back to that in a minute. I have an observation at time t. Okay, so here's t. So say I pick this point. At this point in time, here is my observation. There's a little black dot that corresponds to this point in time, okay? And this observation, say this one, is the additive model, okay? I'm adding together the trend, whatever the trend is doing at this time point, whatever the seasonal, wherever we are in the seasonal cycle at this time point, and whatever irregular event happened at this time point. If I add all of those together, I'm going to get where I'm at on the plot, okay, my observed series. Okay, so I have an observed series, and it's made up of the addition of these ones. Additive models are not always the case. We have cases where that seasonal variation, for example, varies as the trend rises. We see that, for example, with changes in sea level affecting the tidal amplitude. So we can't use additive models in those cases. In this case, we can use an additive model. It's quite clear. The seasonal variation does not change as the level of trend rises. The relationship here is additive. So here's my y, okay, my observed, in this case, CO2 concentration at this time point. And it's got the trend, cyclical component, seasonal component. Sometimes we separate those out because there's more than one thing. Sometimes we don't. We're going to come back to the cyclical component later because there might be more than one. Okay, in this data set, it seems like there's only one cyclical component going through, and it's got a seasonal pattern. But then we have you'll see plenty of examples later where we have more than one cycle. And actually that's, I think, the more interesting thing. So if I take my time series that I just defined previously, and I, in R, decompose it, and it's a type of additive model, what the program is going to do is give me the trend, the cyclical, and the irregular components. So I'll show you what it will spit out. Okay, if I plot my decomposed time series, here is my observed time series. There is the trend, the cleaned up trend. We'll explain in a moment how this is happening. Here is the cyclical component or seasonal component. You'll see these interchangeably, like I said. And this is the amplitude of that change. So I'm changing approximately from the trend. I deviate about 2 to 3 ppm, parts per million, of CO2, and that's to do with the breathing of the planet. Okay, the forest, basically the northern forests. Here are the irregular, random irregular parts of the time series. So if I take this one out and this one out, I'm left with this. And it's quite small, but there are points in time where we have a very strong El Nino, for example. Very strong El Ninos lead to drought, and it affects transpiration, okay, for the trees. So I have more CO2 in the atmosphere because less of it is in the plant. I have periods of, here's 1964, volcanoes. So it's interesting to look at the irregular components because sometimes you can learn something about your system. So we'll start talking about each one of those separately. I'm going to start with the trend, but I'll do it in the next video because I'm sure you need a cup of tea.